Okay, in continuing with the use of the method of Frobenius in developing the Bessel function of the first kind, we have in this next example, okay, we have looking at solving for y, whereupon x squared y double prime plus xy prime plus x squared minus 4 quantity times y is equal to 0. And again, getting this in the form where we can set up the method of Frobenius. Okay, we're going to have the first term to be only y double prime. So if I divide this equation by x squared, we're going to have in the rewrite y double prime plus 1 over xy prime plus x squared minus 4 over x squared times y is equal to 0. And again, from our y prime term, okay, we have the numerator is going to be p of x, which we have equal to 1. And for the y term, we have the numerator, which would be q of x, and that is equal to x squared minus 4. And again, for p naught, that is equal to p whenever x is 0. So again, that's baked in at 1. And whenever x is at 0, we have q naught is going to be q of 0. And whenever we had just x squared as the numerator, q naught was equal to 0. But this time around with the minus 4 that follows, it turns out that q naught is equal to minus 4. And applying what we have with the method of Frobenius, it's going to turn out that for the values of the roots, we have positive and negative 2. And setting up where we can develop the Bessel equation of the first kind, we're going to go with the higher root value, which in this case is going to be positive 2. So we have for y, again, we have y is equal to x to the r1 times the summation as n goes from 0 to infinity of c of n times x to the n, and with x to the r1 set to x squared, I'm going to multiply x squared and x to the n. So we're going to have in the rewrite, we have the y is equal to the summation as n goes from 0 to infinity, c of n times x raised to the n plus 2. All right, and now for what we have in specifying what we have in our summations. Okay, so we have for y, okay, you have starting out at n equal to 0, so you have c naught x squared, c1 x cubed, c2 x to the 4th, and like c of 3 x to the 5th, and running continuously. And for y prime, okay, again, we have the summation to be where we have n plus 2 times c of n times x to the n plus 1. And you had just the first order derivative of y, so you had 2c naught x, 3c1 x squared, 4c2 x cubed. And then we have with the derivative of this, we have the second order derivative of y, which we have in summation notation as n goes from 0 to infinity. We had, again, the summation of the product of n plus 2 and n plus 1 and c of n times x to the n, where we have in the mix 2c naught plus 6c1x plus 12c2x squared. And taking these sets of terms into what we have in the equation, and we're going to combine like terms and arrange. All right, and I did a little bit of a shortcut, and we have 5c1x cubed, 12c2x to the 4th, and we have also c naught x to the 4th, c1x to the 5th, c2x to the 6th, and so on. And again, we have is equal to 0. And so again, so we have the differential equation, okay, set equal to 0. And we have among the sets of terms, now the lowest order term is going to be 5c1x to the 3rd. There is no other cubic x expression that exists. And if I set this to 0, c of 1 is automatically equal to 0. And we have the same domino effect as what we had earlier. And we have all the other odd-valued subscripted constants, which will end up at 0. And as for what we have with the even subscripted values, okay, we have 12c2 plus c naught is equal to 0. And we had that co2 is equal to negative c naught over 12. And combining, okay, what we have for what were the 6th order terms. So we would have 32 CO4 plus CO2 is equal to 0. And we have CO4 is equal to negative C2 over 32. And in terms of C naught, now we have C naught over 384. And for c of 6. Now I have 60 c of 6 plus c of 4 is equal to 0. And we have that c of 6 is equal to negative c of 4 over 60. And that would translate out to negative c naught over 23,040. All right, now we're going to have a bit of a different dynamic to be created. And now we're going to be heading out in the direction of the Bessel function. And since R1 is equal to 2, we're going to be looking at a Bessel function of the first kind of order 2. And now, just for what you have in your factorial notation in the denominator, ultimately you're going to have k prime times the factorial, or I should say k factorial times the quantity of k plus 2 factorial. And now for c of 2, okay, now we're going to have negative c naught over 12. And what's going to happen here, now we are going to be working with powers of 2 and also k and k plus 2 factorials. So for c of 2, we have for the breakdown, we have negative 1 to the first c naught all over 1 factorial, and you have 1 plus 2 factorial, which would be 3 factorial. And we have, again, 6 times 2, so we have times 2 to the first. Now for c of 4, I have c naught over 384. And in the pattern, we have negative 1 squared c naught. And this time we have 2 factorial times 4 factorial. And we have times 2 raised to the third. And for c of 6, this is going to translate ultimately out to negative 1 cubed c naught. And we have all over 3 factorial, 5 factorial times 2 to the fifth. And for what we're going to have in the ensuing pattern, we now have c of n is equal to negative 1 to the n over 2 c naught. And we have all over the product of n over 2 factorial. And the factorial of the quantity of n over 2 plus 2. And then we have times 2 raised to the n minus 1 degree. And if we let n be equal to 2k, we're going to have c of 2k is equal to negative 1 to the k c naught. And we have k factorial, k plus 2 factorial. And we're going to have 2 over 2 to the k minus 1. All right, or 2 to the 2k minus 1. So we have for the expression ny, so this is what we had in our setup when we had the summation in terms of the variable n. But as we let n be equal to 2k, I'm going to move the c naught out to the front. And again, we have negative 1 to the k, and we're going to have x to the 2k plus 2. And we have over k factorial, k plus 2 factorial. And we have in the denominator, again, we have 2 to the 2k minus 1. But I'm going to write this expression, 2 to the 2k minus 1, in terms of 2 to the 2k plus 2 to have the degree to match up with that to which we have x to be raised. So we have for 1 over 2 to the 2k minus 1. So if I put this in terms of 2 to the 2k plus 2, this will be 2 to the 2k plus 2 minus 3. And then we have branching out, you have 1 over 2 to the 2k plus 2 times 1 over 2 to the negative 3. And now, say if you have like the constant over 2 to the negative 3, and just set this equal to 1. Now the value of the constant is going to be 2 to the negative 3, which will be at 1/8. So you can think of like this, it's like the constant is at 1/8 divided by 2 to the negative 3, or 1/8 over 1/8, which is going to be at 1. And I'm going to have this highlighted in blue. And then we have just taking what we have here. So again, we have with the numerator, we have negative 1 to the k, x to the 2k plus 2, got k factorial, k plus 2 factorial. And again, branching off from 2 to the 2k minus 1, again, have at the upper end 2 to the 2k plus 2. The other part combined with the constant, okay, that just became 1. And as we look at combining, condensing what we have with x and 2, our exponential bases, we're now going to have the summation as k goes from 0 to infinity of negative 1 to the k all over k factorial times k plus 2 factorial. And you have this ratio times the quantity of x over 2 raised to the 2k plus 2 degree. And for what we have here, this will be a Bessel function of the first kind of second order. Okay, so again, what we have here, again, you have the Bessel function of the first kind where we have in this case that p is equal to 2, so we have the Bessel function of the first kind of order 2 to be the result.